For 6 decades, engineers have meticulously built the most complex machines in human history. They've aligned submicroscopic structures with atomic precision, packing billions of transistors onto tiny slices of silicon. But they ignored exactly half of the available physical real estate on the wafer. If you take a modern processor and simply turn it over, you find a cold, featureless, reflective gray expanse. It is completely blank. Every logic gate, every memory cell, and every piece of active circuitry is crammed into a microscopic grid solely on the top side of the substrate. Leaving the backside blank was a luxury of physics that manufacturers can no longer afford. That empty space is now the only escape route from a thermal bottleneck threatening to halt the progress of computing entirely. The problem started in 2005 with the breakdown of a physical rule called Dennard scaling. For years, shrinking transistors meant they naturally consumed less power. When that rule collapsed, chip components kept getting smaller, but their power densities skyrocketed. Take a look at this animated cross-section of traditional chip architecture, often called the Manhattan grid. The blue lines represent data signals, and the interwoven orange lines are the power delivery network. Both are forced to share the same 15 layers of congested metal on the front side of the silicon. To reach the transistors at the very bottom, electrical current has to fight its way down through all 15 of these highly resistive layers. This friction causes a severe voltage droop, known as IR drop. Up to 30% of the electrical energy fed into the chip never does any useful computing. Instead, it converts into parasitic heat, creating an unsustainable thermal crisis right at the logic layer. The front side of the chip has become a physical prison. To keep transistors firing without melting them, the massive power delivery network has to be exiled to the other side of the silicon. Rerouting this electricity requires an active industrial surgery called wafer inversion. After the top layers are built, the active wafer is bonded to a rigid carrier at 250 degrees Celsius and mechanically flipped upside down. With the blank underside now facing up, manufacturers use brutal mechanical grinding and heavy chemical etching to rip away the vast majority of the bulk silicon. This chart shows the massive scale of material removal. The substrate starts at 750 micrometers. Grinding strips away 99.9%, leaving a fragile membrane under 100 nanometers. At this thinness, intense mechanical stress creates severe risk of fracturing. To stop the grinding process exactly before it destroys the active transistors, engineers embed a chemical brake, a highly precise silicon germanium etch stop layer that halts the removal precisely at the basement of the logic gates. This violent reduction of the physical material is the only way to expose the underside of the transistor network. Now, manufacturers face a massive mechanical challenge. They have to align features from the newly exposed backside to the microscopic frontside structures through a highly stressed wafer with sub-10 nanometer precision. To find the transistors, deep cylindrical shafts called nano-through-silicon vias, or NTSVs, are carved downward through the remaining membrane. These shafts connect to buried power rails, prefabricated conduits installed below the transistors early in the manufacturing process. In this diagram, the via lands directly on the rail. These rails use refractory metals like tungsten to survive extreme forging heat. Once secure, thick power lines are deposited across the backside. Current now floods the tungsten rails, completely bypassing the frontside network. By rerouting the plumbing from below, the signal-carrying frontside is finally liberated from the suffocating presence of the power grid. With the power lines removed, data signals can flow freely through the original 15 frontside layers without fighting for space or suffering from severe electrical interference. This side-by-side diagram illustrates how exiling the power rails impacts the physical layout of standard logic cells. On the left, a traditional cell requires a height of 6 microscopic tracks to fit everything. On the right, separating the power allows the entire cell to shrink vertically to a 5-track height. As the logic pathways compress further, engineers can transition to an ultra-dense 4-track layout. This dramatically increases the number of transistors you can fit into a given area without relying on smaller lithographic printing. Backside power delivery solves the spatial gridlock choking processor design, laying the foundational technology required to push Moore's law into the sub-2 nanometer angstrom era. This microscopic architectural shift directly addresses the massive commercial demands of modern artificial intelligence. Latest AI data center accelerators are pushing power limits toward an astonishing 1,000 watts per chip. Delivering that much current without melting the silicon is why the 3 largest semiconductor foundries on Earth are locked in a high-stakes struggle to master backside power. This schematic compares the 2 leading approaches. Intel's method, called PowerVia, uses tiny vias to reach the rails. TSMC's superpower rail attempts an even more complex maneuver, making direct contact with the transistor's source and drain regions. These different strategies carry immense yield risks. Intel is targeting aggressive volume production by late 2025 on their 18A node, while TSMC has pushed their rollout to the second half of 2026 to ensure the complex direct contact integration actually works. The silent replumbing of the transistor is a massive structural gamble. It is the mandatory physical infrastructure required to keep the next decade of artificial intelligence powered, cool, and calculating.